Thank you. So these are my other engagements, and everything I'm going to be discussing here is based on joint work with Jonathan Stern, Julian Higgins, Ian Reyes, and Sonia Hernandez-Diaz. Okay, so let's talk about immortal time. Immortal time, as I'm sure all of you know, is this period during which a person cannot die. So the person cannot die during that period. So the person we say is immortal during that period. We don't only use this for death. We use this concept for any survival analysis. So any time that the person cannot develop the event of interest, whether that is mortality or cancer or cardiovascular disease, we say that that person is in an immortal period. And of course, because people sadly can never be immortal, if we have an immortal period in our analysis, we are doing something wrong. And that means the survival analysis will be wrong. And that's what we are going to discuss here, why that happens and how we can prevent that from happening. Now, this is a very old thing. It's a very old concept. The oldest mention of this problem that I found is in this book that was published in 1885, and it's based on the research of William Farr for the previous 40 years. And here they mentioned this thing. In fact, there is a page in which this is what the book says. If it were found that the mean age of death of coroners is 22 years, of lieutenants 29 years, of captains 37 years, of majors 44 years, of lieutenant colonels 48 years, and of generals even older, well, a strong case may no doubt be made on behalf of those young but early dying colonels. It would be almost necessary to make them generals for the sake of their health. So this concept has always been there. It's something that people have been, as soon as people started working with observational data, they found this potential problem. And you all can see what the bias is here, of course. When you are a general, you have survived already a long time, right? Now, this is 1850s. You fast forward 150 years, and this is still happening. There is this paper about how Oscar winners live longer than non-Oscar winners. And the paper says life expectancy was 3.9 years longer for Academy Award winners than for others less recognized performers. And they say how this high status confers a large survival advantage. I'm sure you can see, again, it's the same mechanism happening in a paper published in the 21st century. So if you think about this problem, it explains a lot of the blunders of observational epidemiology in the last few decades. A lot of the problems that we have found are some form of immortal time. And of course, this topic became very well known after the first heart transplant studies were published. This is in the late 60s and early 70s. The heart transplant studies, observational studies, found that people who got a heart transplant live longer than people who didn't get a heart transplant. But of course, you have to survive until the time that you get a heart transplant. It's the same thing over and over. Mitzgale in 1971 talked about that, and I'll mention him again. After the heart transplant things, and this was debunked, there are still dozens of papers published in the medical literature that finds that treatments are fantastic. Many treatments are great. I mean, there are papers about corticosteroids associated with a 30% decrease in mortality, beta blockers 60%, statin 70% in cancer. Sami Sousa has written a series of papers on this. Alan Walker here has also talked a lot about immortal time bias and that name. So this keeps happening. And this keeps happening even though we know from the 19th century that this is a problem and we know how to fix it. In fact, Mitzgale, as I said, in 1972 published a paper in which he very elegantly showed what the problem was in the heart transplant studies and proposed several ways of fixing it. In fact, some of the things that I'm going to talk about today can be traced back to Gale in 1972. And then a few years later, Jamie Robbins developed and published his counterfactual theory. If you apply that, the methods that Jamie Robbins described in 1986, it's impossible to have immortal time bias. So there are many ways that we know. This is not new. We know how to solve the problem, and yet this keeps happening. And there is a lot of discussion in the literature about what the bias really is, how to call it, what are the data analysis that we can do, and there is also a lot of insistence in in-person time. That was actually a red herring here. A lot of the ways in which people have proposed to fix this problem is by thinking about person time, which I will talk about later too. Now, a few years ago, some of us published a general framework for immortal time bias. Let's not be humble here. And this says that, okay, if we think in terms of the target trial that our observational studies are trying to emulate, and we think in terms of the eligibility criteria for that target trial, the assignment to treatment in that target trial, and what the start of follow-up, time zero, is, then we can very easily see what the bias is and how to solve it. And we described two different types of immortal time. One is due to an incorrect selection of people, and the other one is due to an incorrect classification of people into the treatment strategies. So I'm going to talk a little bit about these two biases. First, a few words about the target trial. This is the hypothetical randomized trial that we would like to conduct to answer a causal question, but we can't. Therefore, we use our observational data to try to emulate that target trial. And the target trial framework leads to a two-step algorithm for causal inference. First, we have to ask a causal question, and second, we have to answer the causal question. And those are different things. First, we ask the causal question, meaning that we have to be able to describe the protocol of a target trial that we would have liked to conduct. And the second thing is we either conduct the target trial to answer the question, or we use observational data to explicitly emulate that target trial. And explicit is really the key word here. So when I talk about the protocol of a target trial, it's like the protocol of any other randomized trial. It has several components. The eligibility criteria, the treatment strategies, the assignment, the outcomes, the start of follow-up, the time zero, and the end of follow-up, and the causal contrast that we're using. And we use the observational data to try to map each of these design features to the data that we have. If we map it well, we have good data, we'll succeed. If not, we won't succeed. And that is really a very important point here, that by following the target trial framework, we eliminate some biases, but not all biases. For example, if there is confounding, because of lack of randomization, there is confounding and we haven't measured the confounders, we still have confounding, because this is an observational study. But biases that happen because we don't design our observational analysis in the correct way, those are the biases that disappear. And one of those biases is the bias that happens when there is immortal time. So the target trial framework solves that part, exactly that part that is, and this is what I want to talk about now. So let's talk about the two types of immortal time. The first time is the immortal time that happens when we have an eligibility criterion that is defined after the start of follow-up. So, because then we are restricting the analysis to people who make it until that point. And that incorrect selection is what creates the problem. Now, this could happen in a randomized trial, although it will be very strange, but let me give you an example in which this will happen in a trial in which we don't align the eligibility criteria at time 0. All right. So let's say that we have a trial with 60 million people. I don't want to worry about p-values or confidence intervals or anything like that here. So we have 8 million people are assigned to starting treatment, that z equals 1, and 8 million people are assigned to not starting treatment, that z equals 0. Let's just say this is a trial with full adherence and no losses to follow up. I really want to isolate the problem that we are doing. So of the people assigned to z equals 1 to treatment, 2 million died in the first 3 months, 4 million between month 4 and 12. And in the other arm, z equals 0, no treatment, 1 million died in the first 3 months and 2 million between months 4 and 12. So those are the survivor curves for these trials. At 3 months, we see that the survival in the Z0 group is 1 out of 8. And at 3 months, in the other group is 2 out of 8. Those are that's not the survival, that is the risk of death. So if you take a risk of the ratio of that, the risk ratio is 2. In this case, we see that treatment is harmful in the first 3 months. At 12 months, also it's 2, based on the numbers that I gave you. So if you look at this trial, which is like any normal trial, at time 0 is when people are eligible for the trial, and at time 0 is when people are assigned to either Z1 or Z0. So this is fine. This is how we would analyze any trial like this. Now let's say that the investigators delete by accident the first 3 months of data for everyone. They don't have that data. So because they don't have the data, now they cannot reconstruct these survivor curves because everyone who dies in the first 3 years is out of the data. It's not found in the data. So what do they do? Well, they could say, well, let's continue as if nothing has happened, or let's start the start of follow-up. Let's start the follow-up now at month 3 because we don't have the first 3 months. Both analyses will be biased. In the first one, if people say, okay, let's act as if nothing had happened, because now we have lost the first 3 months of follow-up. We don't have that in the first 3 months of follow-up for the people who are left there. So the curves will look something like that, which of course is wrong. Those are not the right curves, and that's the immortal time now. Or they could start at time 3 because they have lost the first 3 months, and the curves are also wrong because at time 3 there is a very big difference already between both groups that is lost there. That is sometimes known as a landmark. So both analyses will not be correct, and if you can see why. Here, assignment happens at time 0, and the same for these other two, but in the right analysis with all the data, we also apply the eligibility criteria at time 0, but here, eligibility is applied later, after time 0, and that is what creates the bias. So the causal risk ratio cannot be correctly estimated, and the absolute risk cannot be correctly estimated. This is just a form of selection bias. It's just that in this case, if we include this, there is also an immortal time here because of the way we define this. But the point here is that the bias is a consequence of incorrect selection based on eligibility that happens after baseline. And the immortal time is a consequence of that. The immortal time is not a cause of the bias. It's really what happens when we do something wrong. If we think in terms of DAX, it would be something like this when we only select people who have survived for the first 3 months, and that creates a selection bias for the risk ratio and also bias for the absolute risk, as I said. Now, this is not going to happen in a trial. Typically, people are not going to delete the first 3 months, but think about observational studies in which we restrict the analysis to those who have survived for 3 months, those who have data for 3 months, those who, et cetera, et cetera. Any time that we apply the eligibility criteria after baseline, then we are in exactly the same situation. Even if the data from the trial from the observational studies look the same as the data from the trial, as I do here, even if the risk ratios are the same as in the trial, once we restrict to people who have survived for 3 months, then we are left with the same situation. Either we do analysis 1 that has immortal time plus selection bias, or we do analysis 2 that has the selection bias. So there is no way to really fix this problem when we make the eligibility criteria not synchronized with what should be the start of follow-up, and it's the same causal graphs can represent that. Okay, so this is also known sometimes as prevalent user bias. It's a type of selection bias that happens because of the misalignment of this thing. And this type of bias explains a lot of things that have been found in the literature that were like the big examples of observational studies that were wrong, like the hormone therapy and coronary heart disease in post-menopausal women. That was an example in which the eligibility criteria were applied after initiation of treatment. If that time between initiation of treatment and when the eligibility criterion is applied is included in the analysis, there is immortal time. If it is not included, it's just selection bias. This is very common. This is something that happens often in pregnancy studies. If you think about a study to estimate the effect of a vaccination during pregnancy on the risk of abortion, let's say that pregnant women are vaccinated around 20 weeks. And then there is a second visit 4 weeks later. But we restrict our analysis to those who have a second visit 4 weeks later. But to start the follow-up from the time of vaccination, now we have 4 weeks in which no one can have the outcome by definition. So this is something that is not uncommon. Although this is not the main type of immortal time. So I'm giving you this first. This is not the main time. Is the main type of immortal time is the one that I will describe later. Now, for this type of immortal time, one could think that it's very easy to see when there is immortal time, because if we include the period between, say, treatment initiation there and the eligibility criterion, well, the curves are flat. So we should see it. In practice, we don't see it for 2 reasons. One is because not everyone has the same duration of immortal time, so they're not flat. And the other reason is because many observational studies don't show the absolute risks. They only show a relative risk or a hazard ratio. But they don't show you the survival curve, so we don't see it. Anyway. And that is part of the problem here, is this overemphasis on the use of hazard ratios that hide some of these problems, because you only see the hazard ratio. And when we are using the hazard ratio, we just see, so the hazard ratio, there is no such a thing as the hazard ratio, even though we say that. It's said the hazard ratio is different at its time. It's a time-varying hazard ratio. So what we call the hazard ratio is a weighted average of the time-varying hazard ratios. Of course, if we have a flat curve, the hazard ratio is 1 for 3 months, and then it's not 1, and now we are taking the weighted average of 1 and not 1. But in the target trial, the hazard ratio is never 1. So the weighted average that we are getting is not correct in this case. So the only way to solve this problem is we cannot select on post-time zero eligibility criteria. It's also very helpful to construct the absolute risk, the curves of absolute risks for every analysis, not presenting only the hazard ratio. Okay, the second type of immortal time is not due to selection, it's due to misclassification. And this happens when we assign people to a treatment group based on information that is not available at time zero. So we look into the future at time zero, and then we assign people to one group or the other based on what happens there. Right? And this is something that could happen in a trial too, but it will be very, very rare. This is way more common in observational studies in which the assignment to treatment is not aligned at time zero. We are using things that happen after time zero, for example. Now, if we think about treatment strategies, we can classify them as point strategies that just is a point treatment that is given at baseline, and that's it, like a one-dose vaccination, say, or we can have a strategy that is sustained over time. A treatment strategy as a sustained strategy in which we give, say, aspirin every day for 5 years. These sustained strategies that are the most common ones in health research, we can classify them into two types. Those that are distinguishable at time zero and those that are not distinguishable at time zero. And I'm going to explain what I mean here. Because we have immortal time when we compare treatment strategies that are not distinguishable at time zero. And this is not a problem of the observational data. It's a problem of how we use the observational data to compare treatment strategies that are not distinguishable at time zero. So let me give you an example of a treatment strategy that is distinguishable at time zero. We compare start treatment at baseline at time zero versus do not start treatment. Okay. If we have a trial that is assigning people to one of those two treatment strategies, and this is a trial with full compliance, we don't have to worry about those things. If the investigators accidentally lose the variable Z that tells you which strategy the person was assigned to, is not a big problem. Because you just look at the data and say, oh, this person starts treatment, so this person was assigned to treatment. This person does not start treatment, so the person was not assigned to treatment. We know the assignment because there's only one strategy that each person can have data compatible with at baseline in this trial. But what if the trial is comparing strategies of the form, start treatment within 3 months of follow-up versus do not start treatment? Now things are different because now we look at the data, we have data on the treatment that people took, and we see this person who is not taking treatment at time zero. Okay, was that person assigned to start treatment within 3 months or start treatment or do not start treatment? We don't know it. So we will not know which strategy the person was assigned to unless we have a label in the trial that says this person was assigned to start treatment within 3 months or to do not start treatment. Now, let's say that we have a trial with 16 million people, so 8 million are this red part here and 8 million are this black part there. So the red people are the treated, the ones assigned to start treatment within 3 months, and the black people are the ones assigned to do not start treatment. Okay, each line is a million individuals with the same data. Now, let's say that in this trial, in which people are assigned to start treatment within 3 months, just to keep it simple, everyone starts treatment at exactly 3 months, and that's this. So at exactly 3 months, the red people start treatment. The black people never start treatment. Okay, so we analyze this data, like in any trial, by comparing the risk of the outcome in this group versus the risk of the outcome in that group, in Z equals 1 versus Z equals 0. This is how it will look if we plot that. There is actually no difference in treatment because, as you can see, they have this exactly the same deaths in both groups, right? So there is no difference. The risk ratio will be 1 because this is a trial and is done in the correct way. The eligibility and the assignment are synchronized at time zero. Now let's say that in this trial, the investigator lose the variable z. Now they don't know who is red and who is black. They just have the data, but they don't know which group they were assigned to. So that's a problem now because, see, there are these two people here, these two red people who died before they were assigned, before they started treatment. So even though they had been assigned to treatment initiation, they never made it to that time. And we don't know, there's no way of distinguishing now whether they were assigned to delayed treatment or to no treatment. So what not to do, as I'm sure you all know, is to move those people to the black group. Those people say, okay, they didn't start treatment, so we put them there. Because if you do this and now do the analysis, we're going to find that getting treatment is better than not getting treatment. It looks like it's better than not taking treatment because we are moving deaths there. By definition now, if you started treatment in 3 months, you could not die in the first 3 months. So we have all that immortal time is now in that group. So if we redefine the label for assignment Z to something like Z star that says you are in the treatment group if you start treatment within 3 months, and you are in the no treatment group if you don't start treatment, then we have bias now. And this is a bias due to a misclassification of the treatment group. As a consequence of that misclassification bias, we get immortal. Okay. So this is how the survival curves look now. It's of course wrong, and the problem is that the eligibility now happens at time 0, but the assignment to treatment is based on information that we don't know until month 3. We are using future information at baseline to classify people into one treatment or the other, and that creates bias. And if we represent that with a COSA graph, it will look something like this, in which we are now using this newly created variable, in which we say you are treated or you are not treated. It's called Z star. That depends both on the actual treatment and whether you survive or not, and that creates the bias here. So that is what not to do. What do we do to solve this problem? So there is a common proposal to solve this problem, which is, what we have to do is to divide people into person times, and then assign each person time to either treated or not treated. Something like this. These people here will be assigned to no treatment to the untreated person time, and this will be assigned to the treated person time. So this way of doing it, which is typically done with the time-varying Cox model and through that, has some problems. One is that now we cannot estimate absolute risks because we don't know really what the start of follow-up is. Another problem is that we have changed the COSA question. And if you ask me which COSA question I'm now trying to answer, I'm not sure. Probably always treated versus never treated, something like that. But it's not like that because the treated are started later compared with the untreated. So it's not clear what the target trial is here. And also, the hazard ratio that we get here is not the same. It's not generally the same hazard ratio that we would get if we were doing the target trial, because the hazard ratio is a weighted average of what happens over time. And now for the treated, the weighted average starts at 3 months. We're not using the first 3 months. So this kind of solves the problem in the sense that we are not going to have a lot of bias, like all these things like the Oscar winners or the military people or all of that. But it's not very satisfying because we don't have absolute risk, we don't know exactly what the COSA question is, and the hazard ratio is not the same as in the target trial. So what we can do, a different thing that we can do is we can change the COSA question. rather than comparing start treatment within 3 months versus not start treatment, we can change the causal question and say start treatment versus don't start treatment. And that is actually what Gale said in 1972, I think. He said that rather than starting following people from what they are first in the heart transplant list, follow people from when they get the heart transplant, and the people who don't get the heart transplant for the same time. So now there is no immortal time before. So that is one way of doing it. And this solves totally the problem of the immortal time. It changes the question. If we don't want to change the question, because we really want to know what happens if people are assigned to start treatment within 3 months. Sometimes that is the actual question, because there is a grace period for treatment in the real world. Then there are 2 ways in which we can do it. One is by using the G formula. And the G formula is typically more computationally demanding when we have time-varying treatments and many time-varying confounders, but it works perfectly here, of course, to solve the problem. If you want to use the G formula, there is open source software at the Causal Lab website for different forms of the G formula that can be used. Or, if you don't want to use the G formula, you can use cloning with censoring and weighting. So cloning means that, because the problem that we have is that at baseline, at time 0, we don't know whether a person is red or black, unless they start treatment at that time, we don't know whether they were assigned to the start within 3 months or start or never start. So what we can do is for every person at time 0 that has data compatible with more than one strategy, we make copies, we make clones of that person, and assign each clone to each of the treatment strategies. So by doing that, we are making sure that the assignment doesn't depend on the future, because at baseline, everyone who has data compatible with the treatment strategy will be assigned to that treatment strategy. So that is the cloning part that makes sure that there is no immortal time. Of course, because that will lead to a situation in which we have the same person under 2 different strategies. If we don't censor people when they stop following the strategy, we could then compare groups. So the second step is we censor people we censor clones when they stop adhering to the treatment strategy they were assigned at baseline. So that's kind of a per protocol analysis of a trial now. And the third step is because the censoring may introduce bias, then we have to use IP weighting to adjust for that bias. But in all of these cases, and this is the interesting thing, either we use the G formula or we use cloning, censoring, and weighting in general. Those are the ways to do it. Now, this works, as I said, because we don't use the future to assign people to one group or the other. But there are some investigators who, when they hear about this cloning thing, say, that's very weird. So I have to make copies of people and assign them to 2 groups, and I don't want to do that. That seems weird. Okay. If you think that that's weird, try the following. Rather than doing that, what you can do, and this is perfectly valid too, is if a person at baseline has data compatible with both treatment strategies, can be either red or black, randomly choose one. So in the observational data, we randomly assign people to one of the 2 treatment strategies. That also works, but it's very inefficient. And in an example where we actually compared cloning with randomly assigning people, this is an example in which we were comparing 2 breast cancer screening strategies. One is stop screening after a baseline screening, don't do anymore, and the other one is keep doing it once a year. But of course, in the first year, you don't know if someone is going to follow the never screening or the every year screening. So we did both things. So if we do this with cloning, we got a hazard ratio. Yes, I'm going to use the hazard ratio here. It's just much simpler. So if we clone, the hazard ratio is 0.78. But if we don't clone, if we just choose people at random and assign them to this, and we do that 100 times, each of those 100 times we get a different hazard ratio because of random variability. So this is what we get each of the 100 times, very wide confidence intervals. Now, if we take an average of the 100 times, of the 100 hazard ratios that range from 0.58 to 0.97, the average is 0.79. So cloning can be seen as the average of that. If we were doing this an infinite number of times, we are just getting, by cloning, the same thing, and if we randomly assign people. Sorry, question there.
Wouldn't cloning lead to artificially narrow confidence intervals? I mean, you are multiplying people.
Right. You have to take that into account when computing the variance. And the easiest way to do that is via bootstrapping. So we don't really count people that way. So the bottom line here is that there is really no such thing as immortal time bias. We have either a selection bias or a misclassification bias that, and as a consequence of that, there is a period in which some people are immortal. But the immortal time is a symptom of the bias, not the cause of the bias. And if we are using explicit target emulation when analyzing the observational data, we are going to naturally eliminate the possibility of that type of bias, because we are always aligning eligibility and treatment assignment at time 0. So when we don't do that, when we don't align eligibility and assignment at time 0, we have many different types of biases. You think about different ways in which we can misalign assignment A and eligibility E when this is time 0, and we can have E and A before time 0, or A before time 0 and E at time 0, or A after time 0 and E after time 0. There are two of those cases in which we have immortal time. These are the two cases that I've described now. So I'm going to finish here. So this problem of immortal time is totally self-inflicted. There is no immortal time in the data. It's something that we make in the analysis. So if we are using data from trials, there is no immortal time because the eligibility and the assignment are synchronized at time 0. And if we are using observational data with an explicit emulation of a target trial, there is no immortal time because of the same reason. So if we make the target trial explicit and follow through, we make sure that no one is immortal. And we don't want people to be immortal because that creates bias. So thank you very much.